Let's grab some stuff, everybody. Here we go. We'll start with this one right here. Let's do this without a calculator. Just do it. I like to just wade right in. Start plotting some points, see what we get. Okay? If you want to build a table off to the side, that would be fine. Or we just do build the table in our heads, that would be fine too. So if theta is 0, what do we get? Start plugging stuff in. You want like a polar grid?
Yes, please.
I got this like graphic thing.
You have that graph paper all the time.
You don't need a.
Who invited you?
I got you. I got you.
See, I got this rainbow graph paper on.
Great, that was new photographer, right? Okay.
Come on, man.
Alright, there's like, there we go, I found all the polar grids I have in here. I don't really, honestly, maybe I shouldn't have put a grid up there, because I don't feel like I need one necessarily. Okay. For what we're going to do, we're not going to go into great detail on this, so, but you plugged in 0, you got 4, yeah?
Yes.
Right? Let's keep going. Let's do kind of all the cardinal directions, 1, 2, 3, 4. Let's do pi over 4. Also, that's not a cardinal direction, but let's hit pi over 4. What do you get? Plug that in. Two times pi over 4? Pi over 2. Cosine of pi over 2 times 4, still 0. Yeah. So at pi over 4, we're here, right there at the pole. At pi over 2, where are we? What is cosine of 2 times pi over 2? That'd be cosine of pi, then times 4. What do we get? Yeah. So if we're pointed in this direction, you've got me facing this way. We're going backwards 4 steps. Isn't that where -4, comma pi over 2 is located? -4, comma pi over 2. Go back to your battleship experience. Okay. 3 pi over 4, where are we back at? 3 pi over 2. Cosine 3 pi over 2. 0. Back at 0 again. Let's just go to the cardinal directions some more here. So we're here. Now we're at pi, or what do we get? Just 4. 1, 2, 3, 4, but in the pi direction. So 4 units out in the pi direction. And then if we're pointing toward 3 pi over 2, what's the, let's just go right there. If theta is 3 pi over 2, what do you get? 4 cosine of 3 pi. -1. So again, if you're telling me I need to turn and face 3 pi over 2, but then walk backwards 4 units, then I think you put me here. Okay. So now let's just review very, very slowly and beautifully what we've just done. We started here, and then we went to here, and then we were here, and then we were here, And then finally, we were here. And then we came all the way back home. Okay? So I want to make sure you see how it's done, not just what the final result is. As we swept around, do you remember doing this? If those who are in doubt, we started here and then we went to here. Really? Yeah. Don't you remember that? Just recall from 60 seconds ago when we asked, where were we at pi over 2? And the answer was down here, right? Yeah, exactly. As we swept around here, this is in fact where we were, right? So that's the way you draw this, in order. And if you put it into your calculator in polar mode and graph this, you can watch it, graph it in that order. Okay? Yeah.
How do you get the one? So didn't you like plug in? Did you like do one of each?
Come again?
Like which points do you find? Like
I used, I mean, really the most important ones here are plug in theta equals 0, pi over 2, pi, and 3 pi over 2 are the ones I plugged in, right? Now I also plugged in, it's also true at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4 that we're back at 0, too, on all of those. So that's maybe worth noting. What do you think? Your first rose curve, friends. Did you graph it on your calculator too, just to check it out? And watch it graph in order this picture. Okay? Alright, well let's graph another one here. This one is a little trickier. Let's do it again without a calculator. Let's pick a different color. Ah, blue. Okay. So can you tell me anything about this guy? For starters, r equals 3 sine of 3 theta. For example, what is the first 3 control? What do you think? This 3 out front. Yeah, that just controls the size of the petals, so that's maybe not rocket science. The interesting thing is where the petals occur, how often they occur, how many are there of them. Although those are questions that are a little harder to answer, right? But there's a mathematical spin that we can put on those questions. If we want to know when a petal occurs, that's asking when is R 3, isn't it? Wouldn't that be a nice way to ask that question? Find out like when a petal occurs. We'd like to know when do we get that far away. For what the value of theta do we get in our value of 3? So answer it. Go ahead. Sorry, 3 theta in there. So when is sine of 3 theta equal to 1, I guess is what we're asking. Well, that happens when 3 theta equals, what do we need here? Pi over 2. Well, that happens when theta is pi on 6, right? So it looks like, I don't know, there's just the algebra is telling us that when we plug in theta equals pi over 6, go ahead and try it if you like. Plug in theta equals pi over 6. I mean, if our algebra is telling the truth here, if you plug in pi over 6 for theta, you will get 3. So I'll plot it. I'll trust the algebra. What do you get, by the way, before we even go any further? What happens when you plug in 0? For theta. 0. Yeah. Now, admittedly, we saw in the last example, the petals also can occur when sine of 3 theta, when 3 sine theta equals negative 3, right? So we might also want to consider when is sine negative 1, and that happens when we're at what angle? When we get negative 1. That's 3 pi over 2. But that means that if 3 pi over 2, we need 3 theta to be 3 pi over 2. We need theta to be pi over 2. Pi over 2. So this is reminiscent of the last problem, right? As we come here, keep in mind, at 0, we're here. As we sweep up the angles, as we come to pi over 6, we're out here. As we're at pi over 2, though, suddenly we're down here. What? If you plug in pi over 2, check me on it if you like, you get negative 3. That's what we just said would happen. So notice how far we've gone so far. We're here, we're here, and now we're down to here. We've only gone from 0 to pi over 2 so far. At 3 pi over 4, I'll just tell you that, or at, excuse me, where would it be? At 2 pi over 3, that we're at 0 again. And then, where are we? We'd like to know maybe where another pedal is. Well, we didn't tell the whole story over here. Where else do we get a sign value of 1 besides pi over 2? When's the next time that happens? Plus 2 pi. What is that? Five pi over 2. So if we divide that by 3, we get 5 pi over 6. All right, so it looks like when we get to 5 pi over 6, we get another pedal. Again, check us on this. Plug in 5 pi over 6 and just verify that that is in fact does in fact give you a value for r of 3. All right, and then when we get to pi, we get 0 again. When we go to 7 pi over 6 is another interesting spot in our life. What do we get for 7 pi over 6? What do you get for 7 pi over 6? You can plug it in. We can plug it. We can find it too over here. When else we might do the same kind of trick here? What would this be? 7 pi over 2. So this is 7 pi over 6, right? We get another place where at 7 pi over 6, we get negative 3. So you're pointed this direction, but you walk backwards 3 units. No, we've already been there, haven't we? So it looks like as we go past pi, we're actually repeating the values. And I'll just say that now. You can verify and keep going if you like. But here's how this went. We started here. We got this value, just to go back in time. We came back here. We got this value when we were at pi over 2. And we went out here. And then we kept repeating ourselves over and over again. All right, if you haven't done it, let's take to the calculator on this. Go away. Green thing. There we go. Okay. All right. So what I encourage you to do is to type in. Well, we'll do both of these here. Well, I don't know, whichever. So let's type this one in first, though. 3. What is 3 sine? 3 sine. 3 theta. Well, we'll do both. All right, over here, do you know how you gotta have to get this ball thing, right? Come on, do the ball. It's important that you do the ball, guys. Do the ball. I'm gonna go to theta min 0, theta max 2 pi. That should be your default probably, and we'll make it be 0.005. 0.005. How about nice and slow? All right, here we go. You may need to adjust your window somehow. So right now we're at from 0 to pi. There. What do you notice happen though? If I do have it the default as 0 to 2 pi, what do you notice happen? It repeats itself, right? Interesting. So, but notice that we could get this graph, you guys, if all we did was go from 0 to pi, we could get this graph, right? You get the whole picture. You can also go from like negative 6 pi to positive 20 pi and see it go around a whole bunch of times if you want. Let's go back and put the previous one in too. 4 cosine, no, yeah, 4 cosine 2 theta, I think it was. Yeah, if you switch that, we'll do it.
Window, like a square, is it
Zoom 5, whatever, yeah, Zoom square, whatever it's called, Zoom square. So check it out, guys. Something wrong has happened.
That's not right.
Do we need to do 2 pi on this one? On the first one, we need 0 to 2 pi on the first one. Isn't that weird? Right. And it only goes around 1 time. All right, it's worth thinking about that for a second here. This was written up here. This was written up here, right? But maybe you didn't read it. So let's just see what's going on here. And maybe it's at first it sounds surprising. This is true. If you're looking for patterns in terms of what's been happening, everyone's clear on how long these are. But it seems still a little bit confusing, I think, to people. Like, what's the role of this number here? It seems like this means that we get 3 petals. But if it's a 2, we get 4 petals. What? On the last one, right? Well, the answer is that we always get twice as many petals as that number is, right? It's just on this one, where'd they land? They just happen to land when it's an odd number. They happen to land back on top of themselves, right? So there you go. So you saw it. I mean, it did draw on the space of 0 to 2 pi. We did have 6 petals. It's just the second set landed. We watched it happen, landed on top of each other. So you can read all this stuff about rose curves, but you can also just feel, well, that just happened, right? We felt what happened. One other thing I want to mention about that too here real quick. How do we get, just for fun, how do we get just this one first petal here? Anyone want to say? Give me some restrictions on theta that I could put so that I only get that first petal on the last problem.
Pi over 2.
We could go to pi over 2 maybe? That was 0 to pi over 2. I want just that first petal or something.
Negative pi over 4.
Negative what?
Pi over 4 into positive pi over 4. Yeah, look at that.
Oh, okay. Oh, there we go.
Wow.
So negative to positive pi over 4. Who said that? That can explain why that makes sense. Negative to positive pi over 4. Stephanie, go.
0 when it gets to pi over 4, and it also gets 0 when it gets to negative.
Did you hear her? I think it's worth mentioning because, again, you want to just make sure, like, when we were talking earlier, like, when does a petal happen? Oh, you mean when is R3 or something? We were asking that, right? Like, when we can actually mathematicize our questions here, right? When does a petal start or end? Well, by that, do you mean when is R0? Isn't that really what you mean? So you could solve the equation for when it's equal to 0, when R is 0. And you'll get negative and positive pi over 4 as 2 among many places when it's at 0. But every time R is 0, we start or stop a petal, right? Or you get a new one. So it's worth saying that. All right, let's jump into these guys. Let's pick purple. How about? Sounds like fun. Okay. This one is, I think, if this isn't the warm up, it's very close to the warm up. Okay, so we saw one like this in the warm up a little bit. So let's just play the cardinal directions game here. If you plug in 0, what do you get? Don't type it into your calculator yet. No. We're doing this in our heads. We're doing this on paper. What do you get when you plug in 0? Yeah, 3. What happens when you plug in pi over 2? Yeah, sine of pi over 2 is 1, so that's 3 minus 2 is 1 in the pi over 2 direction. What about in the pi direction? 3 again? In both the 0 and in the pi direction, this part goes away, right? And then finally, what about the 3 pi over 2 direction? Negative 1? Yeah, it'll be 3 plus 2, right? So one thing before we draw this picture. What is the range of this function? And that's an interesting question, because by range here I just mean what's the minimum and the maximum value that r can be. What's the range here? What's the smallest r value? What's the smallest r can ever be out of this equation? 1, right? What's the largest r will ever be? 5. Can you see that just from the structure of the equation? And the range is something back in the day that you would have pictured if we were graphing y equals 3 minus 2 sine x. You would have pictured that by being like, okay, well, it's going to stay, y is going to stay in between these dashed horizontal lines, y equals 1 and y equals 5. It'll, like, the whole graph will live in between those two dashed lines, won't it? You ever doing that? You can draw, actually that was usually your first step, is to draw those two lines. So here we can maybe do the same kind of thing. By r equals 1, what we mean is it will never come inside of that circle of radius 1. And by r equals 5, we mean it will never go outside of this circle of radius 5. Right? And so the entire graph that we're about to draw, we can say, lives inside of that annular region, right? This donut-shaped region. So here we go. I'll just graph it with you here. So we started here, then we went to here, then here, then here. It's kind of like a circle that's been punched, you know.
That looks like an apple.
Right, like, graph it on your calculator if you want now. Just check to see what you got here. What's the, let's put a few points on this one here too. So start plugging some points in. 0, plug in first. Yeah, 1, 2, 3, 4, 5. Uh-oh, that's the problem. 6. What about pi over 2? Cosine of pi over 2 is my favorite. Yeah, this goes away. When else do we get 2 as an answer? Besides at pi over 2, we get r equals 2. But also 3 pi over 2, we also get 2. Right? At 3 pi over 2, plug in 3 pi over 2, this also goes away then. What about at pi? What do we get there? Negative 2? Whoa, okay. Let me ask, in fact, let's stop and ask, what's the range of this one? What's the smallest that r can be here and the biggest r can be? We've already kind of said it. Yeah, negative 2 and 6. Next question, is r ever 0? Intermediate value theorem on this. Let's go. So if it's,
I remember that.
Okay. It's got to be 0 at some point, so we can just plot it. If you would like, is anyone dying to know exactly for what theta value it's 0?
Yes.
Well, then solve this equation. You who said yes. It's not bad. It's a nice angle. What is it? When is the cosine equal to -1/2?
Wait, no, JK. 5 pi over.
Oh, someone said it now. 2 pi on 3, yeah. It doesn't matter though because it's there, so whatever. But I mean, the point is at 2 pi over 3 and also at 4 pi over 3, we'll be back here at the origin. Okay. So are you ready to graph it? Let's just listen carefully. We started here, then we went here, then we went here actually, then we went here, then we went back to here, then we went here, then we went here.
Oh my god.
Did you not follow that? What's wrong with you? Okay. No, it was confusing, right? Okay. Let's do it nice and slow. Here we go. You ready? This is fun. You're going to like this. Right? So, in fact, these two graphs, guys, are in the same family. Come on, put your phone away, man. Come on. Just out of respect. Okay, these are the same kind of family here, and I think you can see, before I give you any quote-unquote rules from the book, whatever, it just makes sense that these look the way they do. Of course this has an inner loop rather than this one. This one wasn't allowed to come in toward the pole, just based on this. This was, and when we have negative and positive r values, this is what happens. We get this like extra little inner loop in here. Yes, Itai.
This is, okay, is this like how you did like that graph like a while back when you had the Batman thing? Is that how you did it?
I don't know. I wasn't here.
Don't you have to call
Next
them
question.
simple?
I'll call them tonight now. No, that was all done with parametric equations and a whole bunch of different ones. Yeah.
I don't know if this is like a not smart question, but like, why is the lowest possible value of r -2?
Someone answer it.
Because cosine theta is -1.
So this cosine theta has a range of negative to positive 1.
So like 2 plus.
So this is, yeah, so the range will be 2 and then deviating from that by 4 in both
Okay,
directions.
thank you. Thanks, Michael.
All right, I'll go back now to this slide, which I skipped. I don't recommend that you copy all this. If you want to take a picture or something, you can. The slide is already online. I put the slides up ahead of time, and I copied it word for word from the book. So whatever. All right, it's not that valuable. The thing that's most valuable to you is the experiences we just had together, you guys.
That was so much fun.
Wasn't it valuable? Thank you, Serena.
That was.
How do you pronounce that? What?
But let's just go through it and talk about why this isn't needed, okay? All right. So you saw that we get a curve that doesn't meet the pole when A is bigger than B, and by A I mean this is bigger than this, right? That kind of makes sense based on like our range analysis. Of course it doesn't touch the pole. So we covered that. That was like A from the last slide. This situation was B from the last slide, right? The second example on the right that we just did. We kind of covered that, and it makes sense also. If this number happens to be a smaller in magnitude number than this number, well then of course the range will include both positive and negative numbers, you know? And we'll get an inner loop. This is the one we didn't look at yet. Maybe we can do that before we go to it. I don't know. I have one more example that's a cardioid. And that happens when it hits the pole. When they're exactly the same, then certainly we can get 0, but we won't ever get negative numbers. So if that's the case, then it really is very similar to the first one we drew. There's no inner loop. It just comes in and actually touches the pole. You know. Do we need to have this said? It points up if B is positive, or down if B is negative. It's cosine. Cosine is positive, left, right. Okay, well, whatever. How about you just like plug some things in and see which way it points, right? Like just plug in those 4 numbers, and I think you'll already, just by plugging in 0, pi over 2, pi, 3 pi over 2, you'll get a beautiful picture. You'll get a beautiful picture. Okay. What are these called? No, there's a pronunciation guide right here. Guys, it's French. You have to. It's not. So you have to say it with like a little bit of French. Yeah, you have to. Oh, you're not. What do you do? Oh, like this. All right, but you have to say. Yeah, do it, Elizabeth. Go ahead. Oh yeah, okay. Oh, it's a limaçon. Okay. You need to get Mr. Jablon in here to help us. You say, it's a limaçon. Do you know what it means? Anyone? Limaçon. Limaçon. No. Look it up. You'll remember it better. Who's got Google? Or I can tell you, but I don't know. I thought it'd be more fun if you look it up. It means a small creature of some kind. Oh. Well, we could. Actually, I guess I don't have a cardioid down here. That's sad. Yeah, we got to save some for tomorrow, though. You know? We can do it tomorrow.
Wait, no, we can't. We have
All right. So yeah, what does limaçon mean? Did you look it up?
a small creature. That's snails.
Snail. Yeah. I don't know if it looks a lot like a snail, but go for it. I think you're in a good place to do homework 3. Rose curves and limaçon. Nice. Bye, everybody. Practice your French. See you tomorrow. I'm sorry. We're on world school, you guys. Sorry. Don't be so culturally centric.